In this video, I'm going to talk about ion selective electrodes and how they work, as well as pH electrodes, which are a type of ion selective electrode, and some of the limitations of making measurements with a pH electrode. So an ion selective electrode, or ISE, is an electrode that responds preferentially to a single species in solution. So for example, it would respond to only calcium 2+, or only copper 2+. And in general, what happens is that the ion of interest crosses a membrane on the ion selective electrode. This causes an imbalance of charge. This buildup of charge opposes more ion movement across the membrane and results in a potential difference across that membrane that is related to the difference in concentrations of ions on either side of the membrane. This slide shows a generic ion selective electrode where the analyte of interest we're going to call C+. So the setup would look something like this. We have the ion selective electrode on the left, a reference electrode on the right, and both of those are immersed in our unknown C+ solution. Now what's shown below is a close-up view of the membrane itself, as well as what is happening outside the membrane and what is happening inside the ion selective electrode. So there are many different types of ion selective electrodes, but this one in particular is called the liquid-based ion selective electrode because the membrane itself is composed of an organic liquid that contains a ligand, L, which specifically binds to our analyte of interest, the C+. So you can see that within the membrane, the C+ is associated with the ligand, but there could also be a little bit of free C+ hanging around. And in the bulk solution, so where our unknown solution is, where the unknown analyte is, that C+ can move back and forth across that membrane. If it's a higher concentration of C+ in the bulk solution, then it can move inside the membrane. If it is a lower concentration, then some of the free C+ in the membrane is going to move outside of the membrane itself. And that's going to create a charge difference within the membrane or on either side of that membrane. So in the case here, we have an excess negative charge on the inside of the membrane and an excess positive charge on the outside of the membrane. And it's that potential difference that's going to determine what voltage is measured by the electrode, and then that voltage can be converted into a concentration using a calibration curve. So the equation on the right shows the Nernst equation for this particular electrode. So because the concentration of our analyte within the membrane is constant, the change in voltage is only going to depend on the concentration in the analyte solution. So for pH measurements, what we actually use is a glass ion selective electrode, or a glass combination electrode. So a combination electrode is one that has both the electrode that measures the concentration of our analyte as well as a reference electrode all built into one single electrode. So these combination electrodes would look just like the ones that you used in lab when you're doing the dichromate lab. So they would just look the same as that, except inside that housing it would have both the electrode to measure your analyte as well as the reference electrode. So in terms of pH, the indicator electrode is the glass membrane. So the potential difference on either side of a glass membrane is going to determine what voltage is measured, and then the voltage is going to be converted into a pH. So here's the glass membrane, and we have the concentration of H+ outside of the membrane and a concentration of H+ inside the membrane as well. So inside the membrane there's going to be a constant concentration of acid, and the difference between the concentration of acid inside the electrode is going to be different than that outside the electrode, and that difference is going to determine what the voltage is, which in turn is going to determine what the pH is. Now the inner reference electrode in this case is a silver chloride electrode, and also shown here is an outer reference electrode. So now how does the glass membrane measure different concentrations of H+? So think about what the structure of glass is. It's got a lot of SO2 groups on it, and those got negative charges. So the H+ can get associated or can stick to the outside of the membrane. And since the inside of the membrane is also glass, the H+ on the inside of the electrode can also stick to the SO2 groups. So the thing about pH electrodes that was initially thought to happen, but we now know doesn't happen, is that the H+ ions do not migrate across the membrane. Each H+ on the inside will stay on the inside of the electrode. The H+ on the outside electrode will stay on the outside of the electrode. So what happens instead is that the glass membrane has a little bit of sodium in it. And that sodium is what's going to be moving from one side of the membrane to the other and help charge transfer from one side of the electrode to the other. So if we had an internal solution which had a high concentration of acid, so we're showing that as 6 H pluses here, 6 H's, and our external solution, the solution that we're trying to measure the pH of, has a lower concentration of H+. What's going to happen is that as the H pluses migrate and stick to the oxygen groups or the SO2 groups on the glass, that's going to force the sodium to move away from that area of the membrane. So it's going to move from the inner surface of the glass membrane to the outer surface of the glass membrane, thereby transferring charge, resulting in a potential difference between the outer and inner surface of that electrode, resulting in a potential difference between the inner and outer surfaces of the glass membrane, which is then going to be measured by the pH probe. So for pH probes, every 0.05916 volts represents 1 pH unit, and the only variable in a glass electrode is the H plus outside of the membrane. Okay, so this is the Nernst equation for the pH electrode, and this beta here just has to do with the surface of the glass and how it's not quite perfect. Usually we can assume that's 1, but if it's a little bit less than perfect, beta would be less than 1. So to carry out any measurement in analytical chemistry, you have to be aware of the method's limitations. So for any measurement, the accuracy is limited by how good the standards are, how well known that concentration is. And for pH standards, they are known to plus or minus 0.01 to 0.02 pH units. So just from the standards alone, we're going to have a little bit of uncertainty in the pH. We already learned about junction potential, so that's going to introduce about another 0.01 or so pH units. And equilibration time, it depends on the buffering of the solution. So when you're doing pH measurements, if the solution is not buffered, then the pH is going to vary quite erratically. So you want to make sure to have a buffered solution so the pH remains constant and can be measured reliably. And temperature is also going to affect the pH measurement because that's going to affect the equilibrium of any solution that's being measured, even if it's a standard. So measurements must be done at the same temperature, including your calibration standards. A couple other errors. There's one called the sodium or alkaline error. So when the concentration of H plus is low, so we're in a basic solution, say pH 9, 10, 11, for example, but the concentration of sodium is high, the electrode starts to respond to sodium. So sodium ends up being something that interferes with our measurements at low H plus concentrations and high sodium concentrations. So the apparent pH is going to be lower than the true pH because some of the signal from the electrode is coming from sodium. There's also an acid error. So in strong acid, the measured pH is higher than the actual pH. We don't really know why this happens, we just know it does. And hydration is also important for electrodes because dry electrodes won't respond correctly to H+. So when you're doing measurements with an electrode in lab, you should make sure that the electrode is in some kind of solution at all times rather than hanging on a clamp exposed to the air. So the last type of ion selective electrode I want to mention is a solid state ion selective electrode. And these are particularly useful for measuring fluoride in drinking water, but they could also be used to measure chloride, bromide, iodide, cyanide, and sulfide. So in the case of fluoride, how the ion selective electrode works is that the membrane, which is shown here, is made mostly of lanthanum fluoride, so that's LaF3. So that's the main crystal that the membrane is made out of, but the lanthanum fluoride is doped with europium fluoride, EuF2. So doping just means that an impurity is added to the crystal. So because there is one less fluoride in the europium fluoride crystal, that leaves an opening for fluorides to move or to migrate from one side of the membrane to the other, and that allows an electric current to be transferred from one side of the membrane to the other when the ion selective electrode is immersed in a fluoride unknown solution. So an ion selective electrode isn't a 100% selective for the analyte of interest. We already saw that with the pH electrode where it can respond to sodium under certain conditions. So for an electrode that measures ion A but also responds to ion X, the selectivity coefficient K is defined as this equation here. So ideally, the selectivity coefficient is very small, which would mean that the electrode would not respond very strongly to the interfering ion, which is in this case X. So to determine the voltage in the presence of an interfering compound, we use this equation here. So the voltage equals some constant. Okay, beta, again, just has to do with the surface of the membrane itself. And then over here we have the concentration of our analyte plus the sum of all the interfering compounds as well as their selectivity coefficients. So let's just go through a quick example of how to use the selectivity coefficient equation. So with the question as follows, a fluoride ion selective electrode has a selectivity coefficient of K equals 0.1. So in this case, the F is the analyte of interest, the OH minus is the interfering compound. What will be the change in electric potential, E, when 1 times 10 to the minus 4 molar fluoride at pH 5.5 is raised to pH 10.5. So OH interferes with the fluoride ion selective electrode. So the more OH minus there is in the solution, the more the ion selective electrode is going to respond to the OH minus. So we'll use the equation that we saw in the previous slide. So first thing we're going to do is to realize that for N, we have minus 1 because N is just the charge of the ion that we're interested in. And we're going to assume beta is 1. In most cases, it's going to be at least very close to 1. So whether it is 1 or is close to 1 is not going to matter too much. So now what we need to do is to figure out what the voltage of the ion selective electrode would be at a pH of 5.5. So we have to know how much OH minus is going to be in solution and how much that interferes with the electrode itself. So the concentration of OH minus at pH 5.5. From the pH, we can figure out what the H plus concentration is. From previous chapters, we know that the concentration of H plus equals 10 to the minus pH. So that ends up being 3.16 times 10 to the minus 6 molar. And then we convert the concentration of H plus to the concentration of OH minus, and that ends up giving us 3.16 times 10 to the minus 9 molar. So if we were to use this as the concentration of OH minus, that would go right here in our equation where X is, and we'd also have to multiply that by the selectivity coefficient of 0.1. So 0.1 times the concentration of OH minus is going to give us a number of about 3 times 10 to the minus 10. So if you look at this part of the equation here, A is going to be the concentration of fluoride, so that's going to be 1 times 10 to the minus 4. If we're adding to it 3 times 10 to the minus 9, that is really small. It's not going to add anything to our value for the concentration of F minus. So we can ignore this number. So when we set up the equation to determine the voltage, we can just use this here, where everything after the log function is just the concentration of fluoride, and we end up with a number constant plus 236.6 millivolts. Now the constant doesn't really matter, but it's going to be there anyway. What really matters is the 236.6, because when we determine the voltage at pH 10.5, we're still going to have that constant, but the constant is going to be the same, so all that really matters is the 236.6 millivolts. So now let's figure out the concentration of OH minus at pH 10.5. We use the same process we did at pH 5.5, and we get 3.16 times 10 to the minus 4 molar. So that's quite a bit higher than it was at pH 5.5, which makes sense. pH 10.5 is much more basic. So now, this number, even when we multiply it by 0.1, it's going to be on par with the concentration of fluoride, right? The concentration of fluoride is 1 times 10 to the minus 4. Multiplying the concentration of OH minus by 0.1 is going to make it on the order of 10 to the minus 5. So adding the concentration of OH minus, even with the selectivity coefficient, is going to change the concentration of fluoride. So we're going to have to include that in our equation for selectivity. So we have the concentration of fluoride here, the selectivity coefficient, times the concentration of OH minus, and then when we determine the voltage of this particular situation, we have 229.5 millivolts. So the difference in the voltage at pH 5.5 versus pH 10.5 is going to be minus 7.1 millivolts, which doesn't seem like much, but it actually is quite large. So it turns out that if you didn't know about the pH change from 5.5 to 10.5, you would think that the concentration of fluoride had increased by 32%. And we get that from basically this up here. Right? So we have our initial concentration of fluoride of 1 times 10 to the minus 4, but we're adding 0.32 times 10 to the minus 4. So we're giving it a 32% boost in concentration. So the pH in this case has quite a profound effect on the voltage that is measured by this particular electrode. And if you didn't know about it, then that could seriously skew your results. So that's all I have for this section. If you have any questions, please let me know.